Hi guys, welcome to our 11th lecture on our course on photonic devices. On today's lecture we are going to discuss the Venn diagram and other concepts related to PN junctions. So in order to make useful devices, it's often required to have PN junctions in the semiconductors. In other words, junctions where you have p-type semiconductors and n-type semiconductors on the same device. And this is true for electronics as well as for optical devices such as, for example, lasers, LEDs, and photodiodes, which are solid-state based, fabricated in semiconductors. All these devices can be fabricated using PN junctions. So in these devices, when we say that you have a PN junction, we mean that the p-type semiconductor is in direct contact with the n-type semiconductor, forming an interface between these types of doped materials. In order to properly understand the physics as well as the functional characteristics of these devices, it's important to understand the behavior of the Venn diagram of such PN junctions, both when the junction is not polarized as well as when it's directly or reversely polarized. The main techniques used to dope semiconductors in order to make PN junctions are diffusion, ion implantation, and epitaxial growth. So in diffusion, the material is selectively deposited on the surface of the semiconductor chip or wafer, and by placing it on a furnace at high temperatures, this material which is on the surface diffuses into the semiconductor from the surface downwards. In ion implantation, the dopants are accelerated towards the substrate in certain regions of the substrate which are unmasked by selectively masking the complementary regions with photoresist or other types of masking material. So you accelerate ions using special machines towards the substrate, and they penetrate the substrate. Finally, in epitaxial growth, the semiconductor is grown with the dopants already incorporated into the films. So for example, you have CVD, chemical vapor deposition techniques, where you use gas in order to make films on the surface of a substrate, and in this case the dopants are already in the composition of the precursor gases which will form the solid film. When talking about PN junction, it's important to distinguish between Homo junctions and heterojunctions. So in Homo junctions, the semiconductor is doped with both acceptor impurities and donor impurities, and we're talking about the same piece of semiconductor here. So you have, for example, one single material which can be silicon or any other semiconductor, and you dope this material with different types of dopants. So acceptor impurities for p-type material, donor impurities for n-type materials, and so on. Right, and you can make wells. The substrate itself can be doped, so lightly doped or something to that effect. But you're talking about the same chip, the same piece of semiconductor. So these are Homo junctions. In heterojunctions, different materials, usually having different band gaps, are used to form the PN junction. So for example, you have a junction between aluminum gallium arsenide, p-type aluminum gallium arsenide, and n-type gallium arsenide. Okay, so you have different materials. So for example, you have a film of one material which can be aluminum gallium arsenide, and then you have another film of gallium arsenide, and these two guys are two different materials, right? This one has aluminum and this one does not. In the compositions of the material itself, they have different band gaps, whereas here silicon will have the same band gap whether it's doped with p-type or n-type semiconductor. These two films here will have different band gaps, and they can be doped, right? For example, this one can be a p-type material and this one can be an n-type material, so you have a PN junction, but it's formed between two different materials, whereas here in the Homo junction you have only one material. So let's recall some concepts that we have already seen about n-type and p-type semiconductor. So in an n-type semiconductor, the Fermi level as well as the Fermi function is shifted towards the conduction band. So if we look at the Venn diagram, right? And you have, conduction and valence band. Let's draw these right here. So conduction band and valence band in the forbidden gap. The Fermi level is shifted towards the conduction band, so the band edge right here. So this would be the Fermi level, and the Fermi function, if you plot it, right, f of e is shifted in the same direction as well. So you have the Fermi function equal to 1, and it drops down, and right at the Fermi level it's 1/2 right here, and then it goes down like this. And this means that there's a large probability of finding electrons in the conduction band, and the carrier concentration of electrons in the conduction band, which are electrons are the majority carriers, this is large. So we saw that if we took into account the density of states, the carrier concentration looks something like this, right? Something like this. And it would be small in the valence band because, the probability of occupation is small. So let's recall that this is proportional to the distance between the Fermi function and f equal to 1. So you would have a very small hole carrier concentration here and a large electron concentration in the conduction band. So you have lots of electrons. The probability of occupation in the conduction band is large. The probability of occupation for holes in the valence band is small. For p-type semiconductors you have the opposite. So if we draw the band diagram with the conduction and valence bands here and here, the Fermi level is shifted down towards the valence band, so this would be EF, and the whole Fermi function would be as well. So if you plot f of e, it would be half right around here, and it would drop down. So you have a small electron carrier concentration here, a small carrier concentration in the conduction band, but a large hole carrier concentration in the valence band due to the large difference between the Fermi function and f equal to 1 here. Okay, so you have an excess of holes, which are the majority carriers, and a small amount of electrons in a p-type semiconductors, whereas in an n-type semiconductor you have lots of electrons and a small concentration of holes. So now when we have a p-n junction, you have the p-type semiconductor and the n-type semiconductor in intimate or direct contact here. And this means that these materials are in contact in the atomic level. Therefore, electrons that are in excess in the n-type material can now move towards the p-type material. So this happens as soon as the junction is formed. In holes, which are the majority carriers, which means that you have an excess of holes in the p-type material, they can now freely move to the n-type material. So the excess free electrons in the n-type material diffused, and this happens in the region close to the junction itself, they diffuse to the p-type material because the electrons are in excess in here and there are few electrons in here. So by simple diffusion the electrons will move from the n-type material to the p-type material. The excess holes in the p-type material, on the other hand, will diffuse to the n-type material because, again, you have a lot of holes here and not so many holes in here. So you have holes moving from the p-type material or diffusing from the p-type material into the n-type material close to the junction region here. This charge carrier movement means that there will be a current, right? And by convention, the electric current is associated with the movement of positive carriers. So you have a diffusion current in the direction of movement of holes. So we can write E diffusion, which is associated with this diffusion movements. And notice that both the movement of holes and electrons contribute to the same current, you know, from the right to the left here in this case. So this is the diffusion current, the current associated with the fact that both electrons and holes are diffusing across the junction due to the difference in carrier concentration for these two types of carriers along the both sides of the junction. Now, what happens also is that when electrons diffuse to the p-type material, they leave behind positively charged immobile ions. So when these electrons move here, they will leave behind ions that are positively charged, and we're going to represent them in this way, right, in the n-type material close to the interface. Why does this happen, right? Let's recall that when you dope an n-type material, you introduce donor impurities, for example phosphorus, which has 5 electrons in the valence shell, so this additional electron, and the fact that this guy has moved across the junction to the other side, to the p-type material, has left this phosphorus atom without this electron. So it originally had 5 electrons in the valence shell, and now it has 4. So originally it had 5 electrons in the valence shell, and now it has 4. Therefore, it becomes a positively charged ion because it has 1 less electron. So originally it was neutral. Since the electron, you know, went away, moved across the junction, now it has only 4 electrons and a net charge which is positive right now. So you have these positive immobile ions. So similarly, when the holes diffused from the p-type material to the n-type material, so when this happens here, right, which also contributes to the diffusion current, they leave behind negatively charged ions in the p-type material close to the interface. So you have, these are ions, right? When I draw them like this with circles, it means that they're not electrons, they are actually ions which cannot move. And let's recall what happens when you dope a p-type semiconductor. So this is a p-type semiconductor, silicon doped with boron atoms, which have only 3 electrons in the valence shell. Therefore there's an absence of an electron here, which corresponds to a hole. But when this hole moves to the other material, or in other words, when it moves to the n-type material, this simply means that an electron, which was, for example, right here, will occupy the place of the hole. So the fact that the hole moves just means that 1 electron from the surrounding atoms will move into this hole and occupy this spot right here, and there will be no longer an electron here, so the hole is right here now. It is as if the hole has moved, and in this way the hole will move, you know, across the crystal, across the lattice, across the semiconductor into the n-type semiconductor. But now in this state the boron atom has 1 additional electron right here. So instead of having 3, which was the case when the boron atom was neutral, now it has 4, and therefore it's now a negatively charged ion because of this additional negative charge, which is the electron. Okay, so these correspond to the negatively charged ions in the p-type semiconductor side right here. Now actually, when the electrons move from the n-type semiconductor into the p-type semiconductor, they will recombine with holes here, and these immobile ions will be formed. So they will recombine, right? They will fill the place of the holes, and there will be no more free electrons or free carriers. The same thing will happen when holes move to the n-type semiconductor side. They will recombine. You'll only have immobile ions on either side, so positive ions on the n-type semiconductor, negative ions on the p-type semiconductor, and no electrons or holes, so no free carriers which can move around across the semiconductor. And this means that, you know, there will be an electric field in this region because you have positively charged immobile ions here, negatively charged immobile ions here. These regions are no longer neutral, this region has a net positive charge, this region has a net negative charge distribution, as opposed to what happens in the remaining parts of the semiconductor, where the overall net charge is 0, right? Here there is no net charge, nor here, so there's no electric field in this region or this region. But here, you have immobile ions, and this means that you have an electric field in this direction across the junction, right? From the positive charge to the negative charge, as we know from the laws of electrostatics, there will be an electric field, which I've just drawn. Now I'm using cursive E here in order to distinguish between electric field or electrostatic field and energy, right? We have been used capital E to represent energy. So this here is an electric field in this direction, from the positive charges, the immobile positive ions, to the negative charges. You have this electric field, and note that this electric field will tend to make the holes move along the direction of the field itself, right? So it will tend to make the holes move in this way, and the electrons, which are negative charge carriers, will move in the opposite direction with respect to the field. So electrons will actually move this way, right? This is in opposition to the diffusion current. So due to diffusion, electrons would tend to move to the right, but now this new electric field which arose here will make the electrons move in the opposite direction, and the same thing will happen to holes, right? Due to diffusion, the holes would move to the left, but now with this new electric field that is formed because of the immobile ions, they will tend to push the holes, to the right. So you have a new current which is associated with this electrostatic field. So the direction of the electric field is opposed to the diffusion current, and E generates a new current which is called the drift current. So associated with this electric field, and because of it, there will be a current. Let's use a new color here, which will be in this direction, and this will be the drift current. Now the drift current is associated with the electrostatic field that has been formed in the depletion region. Depletion region because it's the void of free carriers. So you have a drift current, from left to right here. The diffusion current, let's recall, was in the opposite direction. So I diffusion was towards the left, and now you have the drift current due to the electric field of the immobile atoms from left to right. As time goes by, the junction will reach a point where there is a state of equilibrium. So when the drift current is equal to the diffusion current, you have the same amount of free carriers moving, from right to left as you have carriers moving from left to right. When this occurs, the depletion region will no longer grow because, with the diffusion of carriers, the region started growing from the junction. But as the diffusion current reaches a point where it's equal to the drift current, the depletion region width, the width, this width here, right, which we'll call W, will no longer grow. It will remain constant. So the junction has now reached equilibrium.